Hey guys, welcome back to my channel and welcome back to yet another video. Today is a very interesting topic. Today we'll be talking about MLOps, which seems to be everywhere these days. And but in particular, we'll be talking about this paper that you're seeing on the screen, using anti-patterns to avoid MLOps mistakes. Before we look into this paper, maybe it would be useful to think and talk about what MLOps is. MLOps usually is the end-to-end process of deploying your machine learning model into a production system, right? So we've so far seen a lot of talks and a lot of blog posts and everything being written about how to create a machine learning model or how to build a machine learning model. But now the focus is more towards how can you operationalize it and how can you make sure that you can use it in production. So MLOps focuses on that bit of the entire ML ecosystem, and this is something that is becoming very important as ML systems mature these days and are being increasingly deployed in production. This paper was very popular recently, and a lot of people were sharing it around. This talks about using anti-patterns to avoid MLOps mistakes. This was a paper written by a host of different authors. In today's video, we will go into what this paper is talking about very quickly so that you get the gist of this paper, and also hope to take some key takeaways on the different kinds of anti-patterns that you can avoid so that your ML ops systems really perform well, right? Your ML systems really perform well when you have deployed them. So this is a video on this paper. So all the learnings that you see in this paper, in this video rather, are derived from the paper itself. So without further ado, let me just quickly get started with what the paper is about. The folks of the people who authored this paper work in the financial domain. So this is mostly financial ML operations, and then there are a lot of different ML applications in the finance domain, right? You have credit scoring, you have risk profiling, you have loan prediction, and so on and so forth. So this is the authors of this paper work in that domain. So in particular, this paper talks about financial MLOps, and particularly to a subsection of machine learning. They refer to supervised learning or forecasting models. Supervised learning models are where you have labeled data, and forecasting is where you're trying to forecast something in the future, right? So they are in particularly talking about operationalizing these kind of models, not unsupervised learning or reinforcement learning kind of problems. What is an anti-pattern, right? Before we go ahead and start looking into what the paper describes as different kinds of anti-patterns, what is an anti-pattern? An anti-pattern describes defective practices and methodology. So in general, when we talk about software engineering, you would find lots of articles on best practices as to like, hey, what should you be doing in order to build a sustainable and in a good system, right? So these are the best practices that you should be following. Anti-patterns is the opposite of that. So you should be basically trying to avoid these defective practices and methodologies so that your systems can be good in production whenever you deploy them, right? So what we will see now are different anti-patterns that you should typically try and avoid according to the authors of these papers. And these, they say that they've come up with these insights by, of course, researching the state of the art around ML ops, and of course some of their learnings while deploying ML systems in the financial domain. Okay, so let's move on to the 9 commonly practiced anti-patterns that are mentioned in the paper. And this is a screenshot from the paper itself. So they have these 9 commonly practiced anti-patterns that we will look into in detail as we go. But here's a gist of what it is, right? So you have different stages. You have design and development, you have performance evaluation, you have deployment and maintenance. These are the different stages of your machine learning system that you're trying to build. And at each stage, you have a different kind of an anti-pattern that results in. So in the case of design and development, you have data leakage, tuning under the carpet. So these are the 2 anti-patterns. Then you have performance evaluation, you have PEST, bad credit assignment, grade your own exam. Deployment and maintenance, you have act now, reflect never, set and forget, communicate with ambivalence, data crisis as a service. So now if you just look at these names, I'm sure you don't understand most of what they're trying to say because these names are sort of cryptic. And this is what we will see in the next part of the video, where we talk about each of these anti-patterns in some depth and then try and understand what the authors are saying. So the way I've structured the rest of this video is that we will take a look at each anti-pattern and the kind of problem that that anti-pattern results in, and a kind of a solution that could be implemented in order to not do this anti-pattern. Right, so the authors have proposed anti-pattern solutions to anti-patterns in some cases, but in some cases, some of these solutions are my solutions that I think could be implemented to avoid this kind of an anti-pattern. Okay, so now let's move on to the first anti-pattern, which is basically data leakage. Right, so this is the way we will look at each of the anti-patterns. We'll first see the name of the anti-pattern, then we'll see the description, and then we'll see the solution. So data leakage is essentially model making use of information that is not supposed to be seen by the model. Essentially, when the model starts looking at data that it's not supposed to see, data leakage happens. And there are different kinds of data leakages. There's peekaboo, there's temporal, there's oversampling, there's metrics from beyond. Peekaboo is where the model is already taking a peek into the test data set. So when you're trying to build your machine learning models, what you typically have is a training data set, and then you have a test data set, and then you have a validation data set which you use later, right? So peekaboo is perhaps where your model is seeing parts of your test data set, right? Which is not something that you want to do, because you're building your models on your training data set, and if it starts doing peekaboo with your test data set, it's a problem. Because it starts influencing, because you use your test data set to be able to measure the performance of your model on your training data set. And when you say that, when your test data set is part of your training data set, it's a problem. Temporal is a problem, usually comes in the case of building forecasting models, where you're trying to forecast something that will happen in the near future or sometime later. Usually this is a problem of splitting by date, right? So when you have, let's say, data for 6 months, January to say June, and then your training set is, you split your training and test set without taking into account the month, for example, right? You just bundle in all your data and then you just do a random 80-20 split or random 70-30 split. That could be problematic for a forecasting problem, because you don't want your future data to be part of your training data set, because that is what you're trying to basically predict or forecast, right? So that temporal data leakage is where basically you have your test set as part of your training data set. So you don't want future to be part of your present or rather part of your training set. So that results in a temporal data leakage kind of a setting. Oversampling is a very interesting one. So when you have sort of an imbalanced class, you can perhaps try and oversample without splitting your data sets. Or rather, let me put it this way, right? So when you're doing supervised learning, you have different classes. Let's take a binary classification example. You have two classes. One class has a lot more samples than the other class. So in this case, one remedy to be able to fix that is people try to oversample, and there are different ways of oversampling. There's random oversampling, there's smart oversampling, etc. So when you try and oversample, you can perhaps do that without having your train test splits, which will perhaps result in a problem, because you are inferring, or rather you're taking in information from the set that on which you want to predict. Right? Again, the similar kind of a problem that we saw in peekaboo and temporal, but the kind of a problem setting here is different. Here you're oversampling the minority class without your splits, and then basically using information from where you're not supposed to, where you're going to test. Again, that's where data leakage is happening. So all these are examples of data leakage. Metrics from beyond, this talks about how when you're doing some sort of pre-processing on your training data set, like maybe you're trying to do normalization, right? When you use your entire column without again making the split, you use information from your test set to be able to calculate the mean and standard deviation. And that is not very good practice, because then you're using information from the kind of data that the model shouldn't have seen. So, and exactly that's the first line, right? Model makes use of information that it's not supposed to have seen. So if you're doing pre-processing, if you're doing some transformation on your data set without having made that test split, and you're using that as part of your training data set, that could lead in data leakage, right? So what is the remedy to all of this? It is to make sure that to check for all of the above while building your data sets, right? So you have to be very cognizant of the problem you're solving, if it's a forecasting problem or not, or if it's something that has an imbalanced data set, right? Or if it requires some sort of feature pre-processing. And then once you know that you might need all of that, make sure that you're not leaking information from your test set into your training set. And then again, using the same trained model to check the performance of your model on that test set. Because then it's clearly being affected because you have that part of that data set in your training set. Not directly, but indirectly. Like for example, when you're doing normalization, you might not directly have the samples, but you might use data from your training set to calculate the mean, right? So this is sort of indirect data leakage that you would not even realize. So make sure that you are cognizant of all of these different kind of data leakage that could happen while you're building your different data sets. And this is a learning that even I've had while trying to build different data sets. This is a very important anti-pattern, so to say, but which isn't really obvious, because you can see here there are different ways in which this can happen. But it's super important to remember that this could be one reason for either your model performing really well or really badly, right? So this is an important point to remember: data leakage. Moving on. Act now, reflect never. This is also something that we saw in the third deployment phase. So predictions are sometimes used as is without any filtering, updation, reflection, or manual inspection. And this happens in a few companies where you have created the model, you've deployed the model, but you don't take the time to actually think about the model in production. You don't know what you're doing with the model after you've deployed it. I mean, you're not really doing anything. You're just using predictions as is, like the sentence says, without any filtering, updation, reflections. You're just using it after you've finished development. Now that is good for some period of time, but then in practice, what you have to be careful of are these concepts, or rather these effects that could happen. You could see a concept drift. You could see erroneous predictions starting to come out. You could also see adversarial attacks. And this is a learning that I've had while building ML systems in production, where after a period of time, we started seeing sort of, not concept drift, I'll talk about concept drift, but sort of the predictions going awry. And then we had to see what is happening there and try and fix that. So, and okay, maybe I'll just go one by one. So concept drift is where your target variable distribution sort of changes, right? And then what you were trying to predict itself is no longer valid. And that is the biggest problem of all the problems, because now the way you had structured your problem itself isn't valid. So is that model even useful, is the question then. Erroneous predictions, you can start seeing that the predictions move away from what you expect. The distributions of, say, predicted probabilities would change, and you would see things changing. So you have to be careful about how is this model performing in production. Adversarial attacks, these are perhaps some sort of changes that you could introduce into your model, or rather try and attack the model, and then you will not even perhaps try and figure out what's going wrong there, right? So I think this is often seen in research papers where you have sort of a convolutional neural network, and then researchers are trying to fool the system by maybe changing certain pixels, and then making sure that they fool that system and then go ahead and do what they wanted to do. So if you don't really track and don't really try and figure out why an adversarial attack is effective, you will not be able to act on it. So, what's the solution to this? The solution to this is to have systems in place that monitor, track, and debug deployed models. And this is really critical if you have a system in production, right? So, the story doesn't end when you deploy a system in production. ML systems in production will keep evolving, and this is something that, again, like I said, we've learned the hard way. By you have to keep monitoring, you have to keep tracking, you have to keep debugging every little thing that keeps happening, right? And there are so many variables that you will want to keep looking at. Perhaps I'll talk about what you want to look at in an ML system in production, maybe in another video. But you need to have systems in place to be able to track all of these different metrics. So act now, reflect never is an anti-pattern. You want to act and you want to keep reflecting. Tuning under the carpet. This is an interesting point. I didn't think about it that much, but turns out that this is also an anti-pattern where you have different hyperparameters. So hyperparameters are the tuning knobs that you basically use in all of your different learning algorithms. And these vary by the learning algorithms you use, and in fact play a very important role in your model performance. So therefore it becomes important to carefully document all the steps that you've taken while you're doing your hyperparameter tuning. Now, hyperparameter tuning, personally, I have had a mixed sort of a learning there because sometimes it has worked for me that I mean, oftentimes I haven't seen a lot of increment in terms of the model performance or even the kind of effort that you put in to do your hyperparameter tuning right, and the kind of results you see, they don't match. I think a lot more effort goes into tuning your hyperparameter. I'm not talking about neural networks and different model architectures here. I'm talking about the more traditional ML algorithms. I don't know, maybe it's also a function of the kind of data sets I have had. But yeah, it's about getting your hyperparameters right. And there's also, the paper also mentioned that in the case of XGBoost, one hyperparameter tuned model was giving 3.5% more performance over a not tuned XGBoost. Right? So it can result in significant increase in your model performance. I haven't had that kind of a real differentiating experience, but I've read, and of course the paper also talks about it, that tuning hyperparameters becomes very important. And then again, the point here is not tuning. The point here is you being able to document this and you being able to reproduce this when you want to, say, train another model or you want to use this elsewhere, right? You want to know what are the steps you've taken to get that model performance. Because if you change a few hyperparameters, it might be entirely possible that you don't get the same results that you were getting. And maybe, let's say you've got the best result that your model could get by doing lots of hyperparameter tuning, and there are different ways of doing that. There's Bayesian optimization. There's also, I think, random. I'm not remembering the name of that technique, but there's also another way of hyperparameter tuning. So you can use different random subselection. Okay, well, you can use different ways of hyperparameter tuning and find the best hyperparameters. And let's say your Jupyter notebook dies, the kernel dies, and then you've lost, say, or maybe you've deleted it. Now you're trying to reproduce the same model, you will not be able to get it because you've lost count of, or rather you lost the track of your hyperparameter setting that you had done. Maybe in the case of your XGBoost, or the number of estimators, or your the scale post weight that you had used for imbalanced class classification problem. So all of these things need to be documented. All of these things need to be carefully stored somewhere so that you can use these for the kind of data set that you got the best result for. So tuning under the carpet is sort of an anti-pattern where you don't really give importance to your hyperparameters. I would say do some hyperparameter tuning, see if it is improving results for you. Let's see what's the solution I had for this. So basically create separate steps or function in the pipeline for hyperparameter tuning and document everything. So yeah, just like how you would differentiate different process in your different steps in your entire machine learning life cycle, keep this as a separate step. Keep your hyperparameter tuning very concise. Keep it, perhaps put it in the function. Make sure you document every variation of your hyperparameter tuning so that when you want to go back and really use that particular combination, you can go ahead and access that and really use that in your final model. So yeah, hyperparameters are an important part of your machine learning system. Don't ignore them. Make sure that you have documented your hyperparameters. You make sure that you understand that you will perhaps need them again in the future. This is the third anti-pattern. Moving on to the fourth anti-pattern, it's called PEST, as we saw there and hardly understood anything. It says, and if you read the paper, it says it's a short form for perceived empirical superiority. Now, this is also not very straightforward to understand. So I've written it in my own words. So in other words, it's about reproducibility of results. And I'll tell you why I think it is like that. Right? So perceived empirical superiority. So you sort of see certain results in your metrics, and then you sort of think that, hey, I have broken the state of the art on this, but maybe you have a data leakage, right? So you might have this PEST problem where you see, you sort of obtain certain results on the metrics that you've chosen, but maybe those are not the right metrics for that problem. A typical classical example that people talk about is measuring accuracy on imbalanced data sets, right? Like people say, hey, I've got 99% accuracy on this imbalanced data set. But if you look at the class distribution and if you see how the model is performing on each class in terms of the precision and recall, it's performing well on one class, but it isn't performing as well on the other class because of the imbalance. And you've not worked on the imbalance. You're looking at accuracy and you're saying, hey, I've got really cool results and I've built a really cool model. But then your perceived empirical superiority is wrong because that is perhaps not the right metric. Reproducibility here, I mean, reproducibility is one part, but again, choosing the right metric and being consistent with them with different experiments is what PEST is. And making sure state-of-the-art research paper results are reproducible before using them, because oftentimes what happens is a lot of people claim that they have obtained state-of-the-art, but then when you try and reproduce that paper, you'll run into a lot of problems. So making sure that you validate certain claims on the empirical results that they have obtained, and then going ahead and then just saying that, hey, this is correct, right? Like you need to be clear about what metric you're tracking. You need to be clear about, can you get this result again and again? And if that is possible, then you don't have this PEST problem, because PEST problem comes with faulty metrics and not being able to reproduce your results. So the solution to this is the KISS principle. Start with simpler models, decide on metrics, and do comparison of models before advocating specific techniques. Okay. Bad credit assignment. This is a very interesting anti-pattern. Let me take you through the different points. So it is a failure to find the source of performance gains in the modeling pipeline. So you have your modeling pipeline, you have your features, you have your hyperparameters, you have your model, you have your results, and then you also see, you're trying to figure out where is my model performing well, and you try to figure out, is it because of my features, is it because of my model, is it because of my hyperparameter tuning? So you want to understand the levers because of which your model is performing well. And typically in research papers, you see that they focus more on model architectures for performance gain. Like we build a 100-layer neural network, we build 200-layer, we build 300-layer neural network, and they keep, I mean, I'm just talking about neural network here because that's where a lot of research papers come out these days. But the point is that in academia, in research, people try and work a lot on the model architectures, and then they try and squeeze out different, or rather put out different architectures to get that gain in performance, to break the state of the art. Usually in production systems, it is a result of many different things. It could be about clever data problem formulation, it could be about data pre-processing, it could be about hyperparameter tuning that leads to performance gains. And you want to understand where this performance gain is coming from, so that you can, and that's the solution, right? Understand the percentage contribution of each part of the pipeline and double down on what's working. And this is how you can solve this problem of bad credit assignment. Because if you keep believing that your model is what is leading to this performance, and if it is actually, say, your features, you have a mismatch there. You're not giving the right credit to the right part of the pipeline, right? And vice versa as well. If you keep tweaking your models, if you keep tweaking your feature, or rather, if you keep tweaking your models in hyperparameters and you don't have good features, that is also bad credit assignment. You're thinking that, hey, my performance is not increasing despite me changing all these models and hyperparameters. Hey, maybe your features are not good. So you need to figure out what is working and what is not working, and understand how each of these systems are contributing to your model performance. Grade your own exam. I think it's sort of self-explanatory. You write the exam and you grade yourself. Validation of results accurately is important. And testing and validation data should be sampled independently. Hacking, hypothesizing after results are known, which is basically changing the model based on test set performance. What in a gist, what this point is trying to say is that don't grade your own exam. Make sure your validation set is separate while you're trying to build your models. I didn't know about this term hacking, and I mean, this is the first time I'm here listening. I'm reading this term. Hypothesizing after results are known. Hack is basically when we try and use the test set to improve our model, which is what we often do. But we also need to make sure that we have a separate validation set, and these are sampled independently. There's no data leakage coming in between these different data sets, and that it is very clean when we are trying to develop the model, right? So that your model is not, again, it's going back to this data leakage point, but from a different perspective. Your model is not taking in data from where it is not supposed to see, right? Keep validation set completely separate from the model development process, and that's the solution to this problem. Set and forget. This is also sort of very similar to what we've seen earlier. Core assumption of machine learning pipelines, data generating process generated from IID samples. So what happens is you assume that the data will keep coming in the same, the data generation process will be sort of similar as you keep going ahead. But that is not true, right? You can't just set your pipeline and forget about it. You can't just build your pipeline and forget about it. And this is what it's saying. That is an anti-pattern. There can be concept drift, which we saw earlier, which is the change in the statistical properties of the target variable. There can be data drift as well, where your features themselves have changed now. The kind of the values they get now are different from what they used to get, and the data has changed. So you can't just set and forget. You need to keep updating your data sets. So don't set and forget. Don't assume things when it comes to the generation of your training, test, and validation data sets. Keep monitoring and keep updating your assumptions. So this is an anti-pattern that you don't want to do. You don't want to set and forget. Communicate with ambivalence. Sounds a mouthful, but models often are focused on generating predictions, but they don't focus on communicating information on its own uncertainty. Calibration of model. So bias score must be carefully calibrated in its confidence. What it's trying to say is that try and figure out the characteristics of the model itself. You communicate not just the prediction of the model, but more things along with that, right? So understanding the prediction, interpretability, and confidence levels of models is important. Don't just talk about prediction, but maybe, again, it depends on the kind of problem statement you solve. If interpretability becomes important, then you use a certain kind of model, and then you make sure that you communicate that. Maybe confidence levels of each of your predictions as well is something that is important to you and the team you're working with. So make sure that you communicate clearly what your model can do and cannot do, right? What is the confidence interval, how interpretable it is, and what other kind of prediction it is making. So communicate with ambivalence. data crisis as a service. So data sourced from third parties and vendors often doesn't record the steps in the data generation process. And as a result, reproducing or generating new data with the same steps becomes difficult and leads to issues in model performance. Again, very similar kind of a point where you sort of don't have the metadata, or you don't know the data generation process of the data that you're using. And maybe somebody ran certain steps today, he gave you the output of a file, and that perhaps becomes an input to your one of feature an input feature to one of your models, right? Tomorrow you might need new updated data, and then you go and ask them to do the same process, and now they don't have that stored as a script. Maybe that was the one of analysis they had done and they had that as an output. Now you have a crisis because this is, and maybe let's say this is one of the most important variables in your for your model, and now you don't have that data anymore. So that becomes a problem for you, right? So making sure that your data generation pipelines are accurate, are again, I keep going back to reproducible, but it's really so important to be able to extend your data generation pipelines, to be able to go back to your data generation pipelines and get the data that you need. And I think that's the solution, right? Set up your data pipelines and data expectations with the folks that you're interacting with. Make them understand that, hey, I will need this data on a regular basis. I will need it to be in this format. I will need it to be running the same steps or same number of steps as time goes, right? I want you to not change this part of the pipeline. So making sure you set those expectations with the people that are generating the data, and then get that metadata as well, right? Understand how the data is being generated there, if it is possible. But otherwise, also just make sure that you have an extendable process to keep getting that data that you need. So these were the 9 different anti-patterns that were referenced in this paper. I've tried to simplify them as much as possible. There's a bonus one for you, and this is what we will see next. You're trying to watch this video. This is not an anti-pattern, but this is a pattern. And you will watch the video, learn, and go away without helping the creator of this video grow his channel. Please don't. So what's the solution to this? The solution to this is to subscribe, and just please subscribe, and thank you for watching this video.